So if you get angry at me, bear in mind it's being recorded, so choose your profanity carefully. Ta-da. I think that's working. Yeah, we've got this annoying stuff at the top. That'll be fun. All right, this is not that course. All right, I think we're mostly set up. So I will take roll in a second. And to do that, I actually have to pull this out because I got to expose all your names. You can't see each other. Otherwise, you'll have to get a new instructor. Okay, so I'm in the right room, Math 114. This is Civil Engineering 3305, which is Engineering Fluid Mechanics or Fluid Mechanics for Engineers or whatever it's called. And the prerequisite is, I think you have to go through the first year of engineering and stuff. I don't think any of you are in foundation. Should be defoundated by now. So you have aligned with whatever discipline you're going to suffer through until you change to your next major, and we will go from there. So my name is Theodore Cleveland, Dr. C. Profanity, but behind my back, not to my face. And I've done fluid mechanics before, but not for a while. So if you're hoping to find old material for me, good luck. Next semester, they have me do it again. You will be very popular among whoever ends up in my class. Get a good price for whatever you resell. Okay, anybody, is this their first semester at Texas Tech? Like transfer students kind of people? Oh, cool. Just for grins. Any freshmen in here? Good, you shouldn't be. Okay, most of you should be, let's see, 30 juniors in civil engineering. Taking solids this semester also. Okay, so you're in for a miserable semester, everybody. Can't do arithmetic now, and you make it to the end, you will be able to. So this is the Blackboard interface that it'll look similar to what you see. This is the instructor one, so I have extra special privileges like I go change grades and stuff. And we are section 3. There's nothing in the welcome, so don't bother to look at it. That automatically is there, and you're supposed to populate it. I don't know who you're expecting to welcome. So welcome, everybody. Welcome to the spring 2022 semester at Texas Tech. I hope you had a wonderful holiday break. And on the upside, spring break this year is the whole week instead of just one day. So I'm already counting the days. As I was walking over here, these fellows were coming out of the restroom and they're going, my God, this is a long semester. And it's like a day and a half old. Just wait till next week to have that expression. But I understand their frustration on what has turned out to be a lovely day. Nobody wants to be indoors. So this is your Blackboard interface. And if you click on the syllabus deal, lo and behold, a syllabus comes up. So that was actually just a test for those of you at home. Okay, where's my backup? And the notes that I use, that I lecture from, are here. They go into the title, Fluid Mechanics Notes to Accompany 3305. And then there's a bunch of stuff there. Now, I'll warn you, this left column will get bigger as the semester progresses. We're not going to get by with introduction, basic fluid properties, statics, and pressure, and call it a semester, unless you want to. But that would kind of cheat you on some later materials. The textbook, anyone a betting person? How much you want to bet this is not going to work? And nobody will take that bet. Give me a digital rights management error. Yeah, it doesn't work. So what it's supposed to do is it comes up with a picture of books that you can buy for this class, and the book you want is called, I think it's called Fluid Mechanics. It has a picture of, anyone have it already? It has a picture of a dam with flood coming on. If you get the one, which is the first edition, which is a picture of a propeller, that'll probably work. I don't actually have the edition that's specified for this class. So all the page numbers that are in the syllabus are for the edition with the propeller on top. But I can't imagine they're that different, because the only way to justify going from $85 a copy to $112 a copy is more colors in the pictures. So I mean, I guess I'm supposed to upsell it for the bookstore, and this fall at Discover, I guess we get a kickback from as a university. You probably want a fluid mechanics book in your library for later on. So buy the cheapest copy you can find. Don't rent it. I mean, if you're going to rent it, just don't even bother. Might as well try to fake it. But a fluid mechanics book is something that you probably want to have in your library. It hasn't changed a whole lot in the last 15 or 20 years, but stuff that's 35 years old is probably too old, because that won't have any computational fluid dynamics stuff in it. So something more recent than that. Let's see if I can get back to my Blackboard. Try that one. All right, so that's our introduction. So introduce the Blackboard, done. Part of why I said, is this your first semester at Texas Tech and nobody raised their hand? That means you have already been Blackboarded upside the head. So I can expect you to be able to get that far. Introduce the Jupyter book, which we will get back to in a minute. And then the exercises for the class are in this folder called exercises. Trick name there. And I've got the first 3 up. There's going to be more than 3. I mean, unless you take a collection, you can buy me out. We'll buy ourselves out to spend the rest of the semester having mid juleps out in the patio. But I'm just kidding. The URL link should take you to the actual exercise. And because this has come up in all the other 3 classes today, I'm going to be very disjointed when I see you guys on Thursday afternoons, because this is the 3rd to my last class of the week. So by now I've done 2 computing classes, a water systems class, and something else. And so I don't even know what this class is supposed to be. So if I start lecturing from a different set of Blackboard notes, feel free to let me know, or just be quiet and enjoy a completely different topic. In the various uploader stuff, it should show what the due date is in this upper left-hand corner. I believe it's programmed to let you do 2 attempts to submit something, so don't accidentally hit submit. If it's empty, use those 2 wisely. We'll see how that works. But you put a PDF, and if you're using the Python notebooks, assuming you've had 1330, include those 2. So that's where one set of due dates are shown. The other set is supposed to be shown in the syllabus, and they're supposed to actually agree with one another. But if they don't agree, the ones on the Blackboard are the ones that control all of our lives, yours and mine. Although I'm the one that programmed the ones on the Blackboard. But once a date has passed, it is a monumental pain in the neck, beyond monumental pain in the neck, to change anything on the Blackboard server. So let's go back to the syllabus. So there's the usual mumbo jumbo up at the top. I'm not even sure if this is the university approved wordage anymore, or verbiage, I think is the fancy uppity word for wordage. But we're supposed to be in Math 114, and it looks like we are. From 3:30 to almost 5. So we let you out just in time for the Lubbock Rush 10 minutes. Any of y'all from Dallas-Fort Worth? Houston. So been around Lubbock, they don't even have a rush hour. They have no idea what traffic is here. San Antonio, that was the other place that actually has traffic. I guess Austin has now decided they are the center of University of Texas traffic. But anyway, 10 minutes to 5. If you have to be somewhere else, try to delay it until after 5:30, because then there's no more cars on the road. But from 10 to 5 to about 5:20, Marcia Sharp is congested, University is congested, 19th is congested, the South Loop is congested. And that pretty much is all the cars in Lubbock right there. So keep that in mind. We do not have a teaching assistant assigned to this. Actually, that's a lie. I just found out, I talked to Ms. Gurley, and we do get to share a person. How much teaching assisting they'll be able to do is questionable at 3 hours a week. So we basically have a grader. So I will be sharing information with that person. Once I know who it is and have contact info, I'll put it up here for the class. That's if you're too shy to talk to me, maybe talk to them. Or offer to feed them, they might give you the solutions ahead of time. So the instructor notes, we'll go visit those in a second. So I'm reading this stuff because at the end of the semester, you'll get that online survey. So did the instructor discuss the objectives of the course? And so if you walk out of here today, you cannot honestly say no. Because it doesn't ask, did you understand what he was talking about? It says, did he present it? Keep that in mind. Nothing else will make lawyers out of you. The purpose of this course is to provide engineering students with the fundamentals of fluid mechanics. You should be able to use this foundation for the more in-depth courses to follow. The course shall provide students with a set of tools and concepts. So we'll provide wrenches, screwdrivers, drill bits, and a drill, and concepts that are directly applicable to pipe systems, open channels, pumping plants, and measurement of fluid flows, as well as other related problems that may be encountered by practicing engineers. Take a breath. I copied that from someone. What I expect at the end of the semester that you all should be able to walk out of here is to some extent be able to identify fluid properties and apply them to reasonably important problems that you'll encounter. Be able to interpret conservation laws, particularly conservation of mass and momentum. Energy too, but the first two for sure. Identify and apply systems and control volume methods, which is just an analytical tool. It's a way of creating equations so you can use all that calculus that you've spent a year and a half suffering through. Analyze steady pipe flow and networks using associated concepts and computational thinking tools. So the computing class that you had 3 semesters ago, for those of you that had it, you'll actually get to use some of that because I'll make you. Differentiate and apply principles of dimensional homogeneity. That's kind of a frustrating section. Analyze boundary layer flows and drag for hydraulic analysis. Namely, we'll look at drag of cylinders immersed in fluids. How is that relevant to a civil engineer? Why do you care? That's that interactive part of the class. Someone should come up with an answer. Imagine this cylinder, which is really just a Sharpie for go ahead and writing page so that I can get the bars, is a building bigger than that tall. And you put it here, out here in wherever you build buildings, a field. So it's outstanding in its field. Now you blow wind over it. Wind is made out of air. Air is a fluid. The air passes by the building and there is this interaction between the air and the building. Go ahead and guess a word from physics. It begins with the letter F. German is Reibung, friction. That tries to push the building over. So that is a reason why civil engineers are sort of interested in fluid mechanics and boundary layer theory and drag. We don't get into it in the same way that our mechanical engineering colleagues do, although some of us do. This same building, we now rewind it. That is now a bridge pier sitting in a bunch of water. Go ahead and we generate rainfall in Oklahoma and have it come down the entire Trinity River Basin, and it hits that. And what's that water try to do to our pier? tries to wash it away. And once there's no pier holding up the bridge, what happens to the big cluster of traffic? Because now we're in the Houston area, so there are cars. Boom, they go down in the water, and next thing you know, you have swimming cars. You make the evening news. And if they find out that your name had anything to do with the design, you can rest assured you're going to lose your trailer. So have a few extra trailers that they don't know about, just in case. So that's part of why we care about boundary layer theory. We'll also practice some computational thinking methods. It's just a fancy word. We'll look at some computational things to analyze data and make models of our fluid system. A little bit about sensors and instrumentation, but not much. You'll get that again in the 3105, the lab that goes with this class. And the normal sequence is you take the class and then you take the lab. And that's to give you enough time to forget everything in the class so you can relearn it in the lab in a different way. And lastly, characterize and analyze open channels for steady one-dimensional flow. Again, that's my bridge pier in the stream. The student outcomes for engineering, this is ABET stuff. So when you're asked that question on the exit interview online, you now have to answer, yeah, he mentioned something about that. Ability to identify, formulate, and solve complex engineering problems by applying principles of engineering science and mathematics. And ability to acquire and apply new knowledge as needed using appropriate learning strategies. That is CCMR. Copy somebody else's work. Cite it, acknowledge that you stole it from somewhere. Modify it as you see fit for your problem and go ahead and run it. CCMR. So when you're copying other people's stuff, be sure to cite it. And that doesn't mean during an exam to copy each other's stuff and say, I took it from the person sitting 2 rows over from me because they wrote big enough and I could see it. Outside of that particular part of the game, don't copy on exams. So the computational tools you need or whatever came up in 1330. I'm trying to use Jupyter notebooks entirely. In the past, I probably would have used Excel spreadsheets, but we have a dean's office requirement to get with the 21st century, and they've decided that's the 21st century. When you leave here, you'll go use Excel or whatever your company uses. The principles are the same. The arithmetic is the same. The interface is different. We use bulletin board as your learning manglement system. I really need to respell that as manglement because I think that's just cuter. And then there's a website, which I'll show you the front door. So this is everything for the class is stored here. And this is not a university server. This is by Amazon Web Services. So if you wake up in the morning news, it says that AWS East has been down for 12 hours, you won't be able to get here. Don't sweat it. But that happens a whole lot less than the Texas Tech servers blowing chunks. When you get to work, you get here and they just don't work. And about 3 hours later, I say, yeah, it turns out none of our stuff is working. We'll let you know when it's working again. And I sent you an email on a non-working network. So you never get the information. But you can always get to this if Amazon is up and running. This is not the preferred way to access course content because this is more set up for me. Not that there's any secrets there, it's just hard to navigate it. But the instructor notebook, that's working correctly. You can get to that and you can get to the homework exercises this way. So there's, if something is broken, there's other ways to get here. So that's kind of a worst case side door entry into the system. And I don't think any of the other stuff is actually working. Syllabus link, syllabus is linked. Web tools. Oh, it does go to the toolbox. Okay, cool. Let's see if those are actually running. Somebody pick a temperature. 80, I heard an 80. Cool, the database is working. So the tables in the back of your book, in the back of a book, are accessible through this interface. When you're doing homeworks, you might find that preferable to looking up in an actual book. If you do that, just screen copy that that web run, that will be your CCMR. That way you will have acknowledged where you got it from. Any questions before I proceed to ruin the rest of your afternoon? Yes.
So we don't have an access code for like the monitor. We just have like a company that we can.
Yeah, you do not need an access code for the homework because I make the homework problems up, which is extra evil on my part. Wow, that's supposed to be evil laugh, Halloween style. Because the answers aren't out in the wild unless you figure out what book it actually came from. Then maybe you can find them. Okay, I just told you how to build a watch, and all you did was ask me for the time. You do not need an access code for the homeworks for my class. Any other questions? Okay, excellent. Everybody happy so far? All right, well, let's see what we can do to fix that. I'll go through the syllabus first. I will access stuff by the syllabus. So in the syllabus, where it says that, it says if you're reading this and it's not done yet, that's a message to you and me. The syllabus isn't done yet. I've got the first, I'd say the first 2 or 3 weeks is pretty much good to go and set in stone. So today you have no homework due for this class. That's a relief. Sadly, on Tuesday you do, so I have to get through enough material so that I can comfortably go ahead and let that due date stand. To access the homework through the syllabus, you just click on the doodle and you get the homework assignment. But it looks like I don't have the lessons linked. Not only does it look like that, I definitely don't. So we'll have to do it the hard way. There's always a way. Okay, so here we go. We shall begin. It is 3:54 and we go till 4:50, so about an hour. Take a deep breath, wake up, calm down, and we shall begin. So we've gone through the overview of the course. There is the listing out of the catalog. The purpose, I just read that to you out of the syllabus. The objectives, I just read that to you out of the syllabus. Yeah, everyone seems to care about grades. So your letter grade, your choice of vowel or 4 consonants, I know most people want vowels, are determined by any quizzes. I don't have any scheduled right now, but if there's a quiz, I'll let you know. It'll be on Blackboard. Blackboard quizzes are easy to take, especially since I have a bad habit of programming them incorrectly where you get infinite tries. And so only the slowest people on the planet can't figure out that if I keep retrying, eventually I'll be able to guess what the answers are for each poem. Exercises, which are the homeworks, and then exams, which are exams. Everything's collected by Blackboard. So we don't have to deal with paper unless you want to. You might deal with paper when you're actually doing it. Just take an image of it, scan it, and use that for submission. There are 5 exams scheduled for this class, and that's like, oh my God, 5, that's awful. Don't be scared. It's more exams, but less per exam, so that it'll be easier. Well, I guess not easier. It's overall it's the same amount as a 2 or 3 exam class. I just don't like to grade a lot of stuff. You guys don't like to have a lot of problems. So I think it's a win-win to have 5 of them. They are independent of the lecture schedule. They'll be posted on Blackboard. I'll let you know. You should get 24 to 48 hours to work on. So no time constraints. All you have to do is have a pulse and preferably be in the class. You should be fine. And I guess I should put attendance up there since I am going to take roll, but in the whole scheme of things, it's not going to, if you don't show up, you will be at a disadvantage. Okay, so on these notes, on this stuff, the notes look like that. And if there's any code that is there for you to use and copy, the copy paste feature should work, and you can copy that and paste that into your own Jupyter notebook to run. If you don't have a Jupyter notebook or know what it is, panic a little bit, but go ask someone who does. They're pretty easy to install and get running. And that's our introduction. So let's go ahead and actually start the class part of the class. So the first lesson is the introduction. Today I want to go through some problem solving and documentation for how I want to do it in this class. And then we will answer the question, what is fluid mechanics? We'll define a fluid and at least get started on some fundamental properties. So problem solving and documentation. The exercises themselves are not just to make your life miserable and cut into your social life. Certainly that's part of their role, but more importantly, they are to help develop a systematic method to solve problems in an engineering context that you're likely to encounter, to help develop some kind of muscle memory. I mean, that's a bad word choice, but it's all I could come up with at 3 in the morning when I was typing this. You're trying to develop the ability to just do problems and not think about what a pain in the butt it is to do the problem, but think about the end game, get to the end. So muscle memory to apply the process. And it gets easier with practice and to become accustomed to documenting your effort. You've documented your effort in a lot of things to get to this point, but we're now, one of the aspects of professional engineering is everything you do keeps a lawyer somewhere employed. You can keep that trailer that you have worked hard to live in by documenting everything you do so that you can blame whatever goes wrong on something else. Because the lawyers will show up and without documentation, oh, I just applied engineering judgment. It says, okay, you're a 27-year-old graduate engineer. Where'd you get that judgment? And you can't tell them you got it out of a vending machine on the first floor of the building you're in. So the way to protect yourself in a legal fashion, as well as be able to figure out what you did 10 years later, is to write it down somewhere. So that is what the purpose of the exercise is, to practice getting used to that. So here's a suggested format, and let me see if I can, oh good, I can zoom in that way. First, we'll just pick an example problem pulled out of my datum, worked out on paper, and it's okay if the pieces of the problem don't make sense to you, although it's pretty unlikely because someone in chemistry class should be able to solve this problem. There's nothing secret magic engineering about it. But let's say we're presented with a particular problem. In this case, we're tasked with finding the total weight of a 17 cubic foot tank of nitrogen at 500 pounds per square inch, and A means absolute pressure. The vessel itself weighs 50 pounds, and the temperature is 20 degrees Celsius. And all of a sudden go, wait, hold the boat. You've just mixed US customary units and an SI temperature unit. Get used to that, it happens a lot. So the first step in our problem solving procedure, I think I had, oh, there we go, I did have it listed out. So here's the 6 steps I suggest you use. State the problem. And that is actually the most important step, especially as you get later on in your career when money's involved. Make a sketch of the situation. And no matter how ugly that sketch is, it helps you think out your problem. So, making a sketch of how heavy a tank is, how do I draw that? Just draw a picture of a tank and label it. That will help you think about what you need to do. List the known quantities, the things that you know, either from the problem statement or because you know them, or because you looked them up in a table somewhere. List the unknown quantities, in this case, the weight of the tank plus the nitrogen that's in it, and then list any governing principles or equations that you think might apply to the problem. If you're like me and incredibly lazy and cynical, you just write F equals MA, sum of the moments equals R cross F, and then whatever the actual important equation is, because then you've covered everything in engineering. But do your best shot on the governing principles. You may find as you proceed through your solution that you forgot something in the governing principle list. once you realize that, just write it when you notice that. So yeah, we need this other equation, and you good. You're documenting your work. And then starting from one or more governing principles, using known quantities, work your way to answer the unknowns. The last part that most people forget, myself included, is to go ahead and validate and discuss your results. Not so much in the problems here. Here we're just trying to get you to practice it. But a lot of times in real problems, you might have to approximate something or make a guess. For example, acceleration of gravity, 10 meters per second is good enough. It actually greatly improves the arithmetic if you're trying to do the calculations in your head. And you get to the end and say, yeah, it looks like our 8-minute space flight with Captain Kirk will work out just fine. At that point in the discussion step, we might want to go back and redo the calculations correctly on a computer using the correct numbers, because all I did was just guess this on the back of a barroom napkin because it came up in conversation. So that's what the validate part is. You don't use 10 meters per second squared as your acceleration of gravity if you actually have a calculator and can do arithmetic. You would do that if you're doing it by hand in your head. You actually, most of the time, you get really close. Your numbers won't be correct, but your conclusion will be. It'll work or it won't. So here we go on a piece of paper. See if I can get it to size right. That's almost readable. So we write the problem statement. That's step one of our problem solving protocol. Obviously, we have to know what the problem is, and we'll be getting it. The problem statement will be the easiest part for this class. Generally, it would be given to you. So there's the information. So before we go to the sketch, which is there, I can't really hide it. What do we know about this problem? We know how loud the tank is. That's its volume of 17 cubic feet. We know what's in the tank, which is nitrogen. We know the pressure of that nitrogen. How many PSIs is it? 500 of them. That's a lot. We know how much the tank itself weighs. It's 50 pounds. And we know we're told that the temperature is 20 degrees Celsius. So now we go to the second step, which is attempt to sketch the situation. Like I said, some sketches are kind of a stretch of your imagination. So here's our tank. I chose the cylindrical tank. Cylindrical tank, because I don't know what else to do, and it kind of looks like a fire extinguisher, which is what gave me the idea for the problem in the first place. So there's my tank. I've got an arrow pointing to it, telling me it's 17 cubic feet. The pressure is 500 psi. The temperature is 20 degrees. And now I will list my known quantities, which are the volume of the tank. A lot of repetition, indeed. Volume of the tank, the pressure, and the temperature. And we also know the weight of the tank, 50 pounds. The governing equations we're going to use here are the ideal gas law, or Pfeffer's, that's how you memorize it. We're going to assume that nitrogen gas at 500 psi behaves like an ideal gas if we know the molecular weight of gas. So the ideal gas law is pressure times volume is equal to the mass of gas divided by its molecular weight, that's the cat mass, times R, which is what pirates say at the end of every word, or RR, the universal gas constant times temperature. And you would have to know that it's written there, temperature is going to be in degrees Kelvin, absolute. Volume would be liters if your memorized value for the universal gas constant is 0.8314 liter atmosphere per Kelvin mole, because you learned that in chemistry class. They made you memorize it, right? They don't make people memorize nothing anymore. We're all doomed if the internet breaks for more than a couple days. Won't be able to. And then the other governing equation that's kind of important here is the total weight is the weight of the gas inside the tank plus the weight of the tank. So what we don't really know is the weight of the gas. So we now got the first three steps of our problem solving process put together. So figure 1 is a screen capture of all that. In my case, I was the author. I used headings underlined to help me keep track of the protocol items. And also, I'm commenting on my simplistic sketch. I find sketching, no matter how ridiculous, a useful tool to organize known and unknown values. Get comfortable with sketching. Sketching is not in a mechanical drawing or something that you did in EGR 1207, 1206. It's a sketch. It's a way of organizing your thinking. And now we'll work our way to the solution. So what we don't know is the weight of the gas, but we do know that the weight of the gas is equal to the mass of the gas times the acceleration of gravity, because we took physics, and that was something that we didn't forget. We also know that we can obtain the mass of the gas by rearranging the ideal gas law. So pressure times volume times molecular weight divided by RT should give us the mass of the gas in that tank. And we remember that R is 0.821 liter atmosphere per Kelvin moles. Now you're going to go hold the boat. You just mixed units up again. It's like, yeah, so what? We'll fix that at the end when we need to. So don't let oddball units scare you away. Convert them, continue with the problem. The one time I would say dismiss what I just said is if you're taking the FE exam. Usually if the units are goofy on the answers in the FE exam, that's the wrong answer. So you can sometimes use units to help you pick the answer, move on to the next question, and get through your 4 hours of misery quicker. More quicker. All right, so we look in our periodic table of elements, or if you're lucky enough to have a t-shirt that has a table of elements, you can just look down like that and find out that the molecular weight of nitrogen is hair over 14 grams per mole. But you remember from chemistry, nitrogen in a tank isn't going to be monoatomic. It's going to form those N2s. So we need to consider every mole of nitrogen in our tank as 2 nitrogens. So it's going to be 28 grams per mole is our molecular weight that we use. So now we need the volume of the tank, but we're going to need it in liters. We need the temperature of the gas. We'll need that in kelvins. And we're going to need the pressure in atmospheres. So every unit in this problem statement is wrong. Converting volume to liters is pretty straightforward. We take the 17 cubic feet, we multiply by, there's 3.28 feet in a meter, give or take. And there are 3.28 times 3.28 times 3.28 in a cubic meter. And finally, there's 1,000 liters per cubic meter. We come up with, after doing all the arithmetic, 481 liters of volume inside our tank. We recall that degrees Kelvin is just degrees Celsius plus 273. So we add 273 to the 20, we get 293. And the pressure might be a little tricky. I have to recall that 1 atmosphere is 14.75 pounds per square inch. So I use that conversion. I'll take 500 pounds per square inch divided by 14.7, roughly 34 atmospheres of pressure inside the tank. And now I have everything I need to recover the mass of the gas. And there is roughly 19,000 grams of nitrogen, or 19 kilograms of nitrogen. But express it in grams, because if it's an illegal substance, it'll look better in your newspaper article about you as you're making your perp walk off to jail. Here we use the various definition of volumes, mass, and the ideal gas law to try to find the sought quantity. And we're pretty much partway into the solution. We realized that we might have needed an additional quantity that was recognizing that we needed nitrogen diatomic. Now we can apply the weight of the gas formula to find the weight of the gas. We know that there is 19,000 grams of gas in our system. We divide that by 1,000 to get it in kilograms and multiply that by 9 meters per second squared to get everything into newtons. So we pretty much using every letter of the alphabet here. 187 newtons of weight. Now we'll convert the vessel weight into newtons. So 50 pounds force is 2.2 pounds per kilo. And then 9.8 meters per second squared gives us 222 newtons of tank weight. Now comes the hard work. Add those two numbers together. For 409 newtons, which is the total weight. And then it probably makes sense to express the total weight back in pounds, because I assure you, anybody in this room, if I told you what something weighed in newtons, you'd look at me like I'm nuts. I got a bunch of grins and chuckles out of that, so yes, I'm nuts. So we take the 409 newtons and convert that back into pounds, and it's roughly 92 pounds. It's what this tank weighs. And that is how to document a fluids mechanics problem. It's kind of what's expected on your homework in this class. If the exams were in class and they were timed, instead of having enough time to do them at your leisure, you would probably dispense with a few of these steps in order to get to the end. But we will avoid that. I intend for your exams to have enough time. They won't be in this classroom, that you should be able to apply the whole process on those problems. And then the last part, the validation discussion. Just as discussion. So we need several intermediate values, especially using R and CAP-M. We need to recognize that nitrogen has 2 atoms per mole. We needed a table of elements to look up the molecular weight of nitrogen. And the final answers have way too many significant digits. So we'll probably just report this as 92 pounds. It's the whole thing. So fractions of pounds at that point. You need to remember to include units with your numerical answers. Some of you will take classes after this with Dr. Rainwater. You forget units and you are wrong. You're not part wrong, it's wrong. It's just wrong. So to save you that, just remember to include units. There's a periodic table of the elements rotated 90 degrees to the right so that it, it didn't work. I knew it wasn't going to work. It's like you have to turn your head on the nitrogen right up here. And somewhere in there it says 14.7. Gold right here. And gold is like $2,200 an ounce right now. So if this engineering gig doesn't work out for you, convert your Bitcoin to gold and go to some nice tropical paradise. Okay, let's do the same example in the Jupyter notebook. Here I'm going to repeat the example. And so this is how you would do it if you were doing it in the notebook environment. Unlike the piece of paper, you got to put your name somewhere. So you put it at the top, our number and date. Problem statement is unchanged, except instead of being handwritten, it is typeset. Big deal. The sketch is probably the hardest part if you're going to document this in a computer tool, because you don't have drag and drop capability. You have to save your hand-drawn sketch as a file. Portable network graphic would be the suggested format. Then you need to go ahead and create a call out to it in documentation, and there is the syntax for it. It's the exclamation point, square bracket, and just list the file name, assuming it's in the correct path. It renders a file. Known quantities, volume of the tank, pressure of the gas, temperature, weight of the tank, just listed out there as comment statements. Unknown quantities are unknown quantities. And then our governing principles. For what it's worth, that is way harder to typeset than it is to write by hand. But that is all our governing principles. Oh, looks like I was doing some editorial commenting with the duh statement. And then finally, the solution. So now the cool thing is the solution in a computer program uses a whole lot less real estate than doing it on a piece of paper. Molecular weight of nitrogen, everything's the same as the handwritten. All the work is there, and then we get to the end, we print out the total weight of 92 pounds. So either of those two methods is suitable for documenting your work in this class. People that are scared of computers will probably choose to do it by hand, but you're probably better off doing it by computer if you can get over that initial fear. They're nothing to be afraid of. They're just machines whose purpose in life is to take your life and money. Other than that, nothing to worry about. In terms of discussion, we probably want a little bit more description in the calculation sequence than what I just listed there, which is calculation after calculation after calculation. We could get fancy and try to embed a database for common gases so that we could solve this for any gas. That's probably overkill for this class. And in actual practice, you'll probably use a hybrid of the two. Paper and some sort of automated computation thing, and that's fine. Just want to encourage you to do that. So any questions before I proceed on the next one? Good. I'm either very clear or I am online ambient right now, and you're all passing out in this somewhat poorly ventilated room. So let's get to some definitions. In order to define a fluid, let's start out with a solid. Why? Because that makes absolutely no sense. So that seems like a good starting point. A solid, if you recall, is a state of matter that maintains a definite shape and volume. Examples of solids in your everyday life. The stuff between your ears. The solid brain. Sometimes it never works right. It's actually like this is probably closer to the truth. This table, that eraser, the wall. I hope that's all. In the context of fluid mechanics, a solid is something that can resist shear force. So we take our solid object here. Here it's represented as a cube, and it crosses cubic period. We apply a force to the top of the cube. You may not be able to see it in the real world, but the cube deforms a little bit until it's generated enough internal resistance forces to push back against that external applied force, and then it stops moving. And then if we release the force, where does the cube do? It goes back to its original position unless we exceed its elastic yield stress, and then it stays deformed, which get a whole 3 more classes on that. So, for the time being, we deform it, it moves a little bit until it can hold all the force. We take it off and it springs back. And as far as we know, our little cube is not hurt the teensiest bit. The amount of deformation, usually use the symbol E, little e, or epsilon. That is a Greek letter of the alphabet. Currently, there are no viruses named after it, but that's likely to change one of these days. Actually, we're past epsilon, so don't worry about that. We'll be able to use it for deformation. That represents the strain. The applied force divided by the surface area, that's shown there in this cube. So this shear force divided by whatever that area is called the stress. It's called shear stress. So stress has units of force divided by unit. Stress has units of pressure, force per unit area. If you know the area, you can, and you know what the stress is, you can recover what the total force is. All right, so remember in my story, we released the stress and the object bounced back to its original position. More importantly, as we apply the stress, and the symbol for stress is tau, another Greek letter in the alphabet. So that has not been used to name a virus yet, but it's eligible because it's a few letters away from the current one. But for the time being, it'll be stress. Is that the strain or the deformation epsilon is proportional to whatever the applied stress is. That kind of makes sense. You push on something harder, it's got to bend more to keep from falling over. And we would write that either as stress is proportional to F over area. It would also could also represent some functional relationship where stress F, excuse me, strain epsilon is equal to some function of stress tau. The important thing is once we have hit the level of deformation that resists the force, it doesn't change with time. So a solid has the property that its deformation is invariant with the time application of the applied stress. Naturally, a fluid probably doesn't have that, or I wouldn't have bothered to write it, right? So let's just summarize what those pictures are trying to tell us. Solid deforms but not continuously. Deformation proportional to the applied stress. Assuming the solid does not fail, then the deformation for all practical purposes is time invariant. A fluid, in contrast to a solid, deforms continuously as long as the stress is applied. The fluid will continue to deform, especially if we make the mental leap that somehow the fluid can supply itself with more volume as it deforms, which real fluids can't. This will work for the time. So here we have our same cube of fluid, and we apply some shear force to it. And how to do that, I just take the fluid involved, and that gives you shear force. And the fluid starts to deform. Well, it turns out that even under constant shear stress, the fluid will keep deforming. So the strain changes as a function of time. So we have the property that the strain epsilon is a function of time, and therefore, if we've got fancy, we would have to write the strain or the deformation is a function of both applied stress tau and how long it's been applied for. And that's the main calculus looking difference between a fluid and a solid. The fluids are time dependent. So to summarize that in words, the deformation amount is proportional to the applied stress and the duration of application. Fluid strain is time variant, and we deal with that in our daily lives more than we know. Because if fluid stress was not time variant, you could empty dirty dishes in an instant instead of when you're throwing the pot of dirty soup out. Maybe it's just me, but some of it doesn't always make it to the sink when you pull the pot out that you just tipped over expecting all the fluid to come out. And it finds, especially if it's got tomato product in it, it will seek out any piece of textile that's white. Because I think there's some sort of unnatural attraction between tomato sauce and white textiles. Back when I used to have a more grown-up job and wore a tie, people would get ridiculed wearing a tie. It must be uncomfortable. They are, I'm sure they are. But I can't count the number of times a cheap tie bought at JCPenney's has saved a nice white shirt so it could be used in the future. And that has nothing to do with fluid mechanics. That's just supposed to be entertainment. Okay, so what is fluid mechanics? Fluid mechanics, this is, I believe, taken directly out of your textbook, is the study of the motion, deformation, momentum, energy, and related properties of materials that cannot resist shear stress. Fluid mechanics has practical engineering utility, and many engineering problems can be addressed directly with fluid mechanics and analytical methods. I love definitions like that. That told us absolutely nothing. Fluid mechanics is the study of how fluids flow and behave, and engineering fluid mechanics is all of the above, plus how do we use it to leverage the world and make things happen that we want. The next part in the chapter of your book talks about continuum mechanics. Because fluid mechanicists studied calculus for years, they don't want that to go to waste, so they decided to treat fluids as something called a fluid continuum. Real fluids are made up of molecules, which are itty bitty little things. They're even smaller than a
Omicron viruses, and they all get together and agree to attack white shirts at a distance. In principle, one could examine the behavior of fluids by tracking individual molecules. In practice, that is probably still computationally impossible. Although we're getting there. Probably by the end of your careers, none of this will matter anymore because we'll just feed everything to density computers. But until then, we represent fluids as this concept called a continuum, and the behavior of the continuum depends upon the size of the sampling. So these funny little tadpoles without their tails, they're actually supposed to be water molecules. So those got to be hydrogen, that's got to be oxygen, not hydrogen oxide, very dangerous substance. You know, if you put it in your lungs and it stays there too long, you'll wake up dead. That's the stuff. It dissolves everything it touches. So if this is our sampling volume, we have space, the final frontier, and a water molecule. Space, water molecule, space, water molecule, space, water molecule. On the average, if we move this volume around, we probably get the same number of water molecules, regardless of where that particular sampling location. And so if we divided the number of water molecules in that by the volume of the sample, we get what we know as density. And it would stay the same regardless of where you are. But you've all had differential calculus, and so they taught you in this very building or online using the online calculus. You don't still do that. That's still do that online calculus. You were lucky you missed out. Maybe it was calculus for people who would be doctors someday. It was horrible. But we learned differential calculus. If this is good enough, getting smaller has got to be even better. Right? We get closer to the definition of the derivative. Well, it turns out the real thing that's not necessarily good. So if we look at this little volume, let's use that for example. Space, density is 0. Water molecule, density is 1. Space, density is 0. That's not a very good averaging volume. So the continuum concept is, we're still talking small volumes, is that it's big enough that the concept of density for the fluid is constant as you move to different parts of the fluid. Unless, of course, the density is supposed to be changing. And there is a hand-drawn sketch to try to indicate the volume size where, so in this range, continuum mechanics works, and that range might be a couple of centimeters up to a few miles. And then at some point, if we get really big, obviously we're in the ocean or we're on land. The whole averaging system goes to pot at the big size. And if we're little here, we're in that case where space, water, space, water, space, water. So this will appear again in some other classes. It's important only as an idea. It's not important that you actually use it. We just assume that continuum mechanics is going to work and proceed. Occasionally, we treat fluids as parcels or particles. And in that, we're in the Eulerian concept, which is what we should take that. Yeah, I'm in class now. What's up, dude? I'll call him after call. So the Eulerian one is kind of what we're used to. We have this area in space, and we keep track of what's coming in and what's leaving. What's going on inside, we don't particularly get all stressed about. But sometimes we do care about that, and we move to a Lagrangian description where we'll keep track of individual particles and paths that they take. Under most circumstances, either one of them gets you to the same end result. But most of the time, the Eulerian is far more practically useful. But occasionally, we care about individual particle behavior, especially if we're doing stuff like air quality. So the fluid parcel or particle approach is exactly what you had in dynamics or will have in dynamics, because we don't take it here in normal work. So you had statics, and in statics you got kinematics, which is how things move around, pulleys and stuff. And then in dynamics, we have spiders on turn. I think that's Dr. Monroe's favorite problem in the history of the world. That's where you get Coriolis acceleration. So you'll see that if you haven't yet when you get there. That's a very Lagrangian point of view. Air quality models are the ones that I know of that treat cubic kilometers of air as particles and see how they move through. And I've used it in hydrology research where we represent depths of rainfall in individual particles, back where they go in the watershed. But those are both pretty specialized instances. Most of the time, you'll be taking a Eulerian point of view, which is cool because you get to use a bunch of old-fashioned names to describe stuff, and that and whatever they're charging for coffee at Starbucks will get you a cup of coffee. How are we for time? Oh, we're good on time. So moving on in the chapter, the next thing that we want to discuss is dimensions. So we've got our three spatial dimensions. We have time, and then we have however many dimensions are in the multiverse. No, not those kind of dimensions, but yes. Dimensions are things that can be measured. So what can we usually measure? We measure length, weight, temperature, how fast something's going, what the time is, how much time has elapsed. Actually, speed has something to do with length and time. Those are dimensions. Most things that we're interested in are expressed in a set of primary dimensions defined either by length mass acceleration or length weight acceleration. Or length weight acceleration. Either one can recover the missing terms for the other. In the SI system or metric system, it's pretty much that. Length mass acceleration, the primary dimensions, and everything else is defined based on that. Temperature and time are special. They don't fit in those categories, but length mass acceleration, temperature, and time describes the entire state of the system. In the US customary system, because it's America and we're different, length weight acceleration, temperature, and time perform the same role. The primary dimensions are used to construct secondary dimensions, and interestingly enough, the secondary dimensions are usually the ones that are far more practical in our engineering lives. A mile is a much more useful measure of the dimension of length than a meter, especially if we're going 60 miles an hour. So, or a mile a minute for those of you at home without a calculator. The units, on the other hand, are how much of a dimension we have. So let's look at this table. Oh, God, they left me props. This is. I hate to be wasteful, but there we go. So we have a table. We want to determine the length from here to here. We're going to measure it in units of masks. One mask, two masks, three masks, 4, 5, 6, 7, 8, and this table, especially if I shove it just so, is 8.5 masks wide. So the unit of this table length is, I just measured. What was the unit? Masks. Excellent. The length of the table, it doesn't depend on the units. If I measure it in feet, I'll trip if I try to put my feet up there. There'll be a different number of feet than there are masks. If I have the conversions of masks per foot, then it totally doesn't matter. So that's all a unit is how much of a dimension is measured, right? This can be 4 masks. put them here and make it look like something. That's how you can really be naughty. There we go. No one's the wiser. If we were to measure this room, the width of the room, let's see what choices we have based on that. We have tables. We can measure how many tables wide the room is. We could measure mass. We got enough mass. I'm sure we could run across the room. We could use tiles. 22 tiles across this room. I don't know if there's 22. I just made that number up. But you get my point. Those are what units are. Then there's this idea of consistent units. That's a fancy way of saying units that actually make sense. So we have the U.S. customers system, or used to be called the imperial system, probably still is consistent within itself. And the SI system, which is called metric, is consistent within itself. But mixing the two can lead to some spectacular errors. So there's this new telescope that they shot up into space. They found $400 billion laying around. They had to burn it up somehow. That seemed like a good way, because no one's going to call them the people on it. But 25 years ago, there was another telescope that was shot up into space. It's called the Hubble Telescope. It had a wonderful, spectacular error because a certain part of it was designed using, it was either in centimeters, it's supposed to be in inches or inches. Probably it was in inches when they were expecting to be in centimeters. So someone faxed over a set of specifications. The receiving builders didn't know that those were inches, they built them in centimeters. Nothing worked right. The thing was a blind design and not be classic. So it didn't work at first. It was a spectacular error. Somebody lost their job and probably their trade with that. And then someone else says, wait, I know a way to spend $25 billion to fix it. We'll go ahead and put glasses in it, which is what they did. They put corrective lenses on it, and the Hubble Telescope's been taking cool pictures of supernovas and crab nebulas and whatever else to take pictures of out in space. I assume it's out in space. It's probably happening inside a computer. We're all being deceived, but that's beside the point. So getting your units consistent systems is important. Get comfortable with having to work in different units and converting them at the end or where appropriate. You'll know usually into a consistent unit system. The argument for a single system is usually it reduces errors because there's fewer arithmetic operations. Every time we convert a unit, we're dividing by something that has a decimal point in it. We don't have all the numbers to the right of decimal point, so we're introducing errors. Many practical cases, we use blends of both systems, so you got to get comfortable with unit conversions. And page 9 of Hibbeler, which is the text, contains some representative tables for conversions. The example above had some embedded conversions. You could make your own. Here's how you could do it if you want to do it in the Jupyter scripting environment. And length US, length SI is equal to length US times 0.3048. Where did I get that conversion factor? I got it from Mighty Internet, so it must be that. And you actually can build online converters. I think I have one built for this. Oh, I do. If you're uber lazy and you click on that, nothing happens. But if you're persistent, it brings up this web page, and that looks pretty cool, almost professional. And let me see if I can get it to show me. Oh, I hate the machine. Tools, browser tools. So that really tricky looking web page is just a bunch of script that does the unit conversions. And let's find one in here. Oh, it's actually done in a function form, so they should be down at the bottom. Let's do, so feet to meters. It takes whatever the feet value is, divided by 3.28 and return is in meters. So that's all the online converter does. It's really not that hard unless this part has a mistake in it. then you're doomed. So the first few you use, if you use online conversions, go for it. That's fine. There's nothing wrong with that. Check the first few of them until you are comfortable with converting to the level of accuracy you want. Because if I were an evil web producer, I would go ahead and put mistakes in mine on the free ones and then get people to subscribe to the one that works. That's completely evil and very Amazonian, if you think of it. Okay, how do I get back to wherever I was? There we go. That wasn't it. Oh, fine. I know how to use this thing. And I think we are almost done for the day. The unit conversions. Okay, the parts of the textbook that are relevant are highlighted there, pages 3 through 14. The syllabus link is here. If you want to look at an old book, here's another book from a while back. Basically, it won't take a genius to figure out that my notes and this are awful similar. It's almost as if he had copied these directly and claimed them as his own, which would be the actual truth. And then if you don't like typeset stuff, you can go get handwritten ones. I have no idea why anyone would prefer that. Those are old handwritten notes. It's exactly what we just did today. So I will see you on Tuesday. Have a wonderful weekend. Try to stay healthy. If you get sick, do not come to class, please. In the past, I would say, even if you get a hangover, don't come to class. Don't expose the rest of us to whatever illness you have. At some point, we'll all be better. You have a homework assignment due Tuesday. I think it's Tuesday at 11:59, Tuesday at midnight. So go ahead and take a look at that. Based on this, you should have no trouble doing it.
That's right. Do you have some time to talk?
Yeah, I'll talk while I'm shut down. Is that good?
Yeah, that's fine. So I just wanted to introduce myself. My name's Alexis. I think I'm your one student here that's not a CE major. I was previously and transferred to university studies.
Are you the honors student?
No, well, university studies and one of my minors is engineering, so
Okay.
that plays out. The reason I'm trying to talk to you is I've never used Jupyter before. I didn't have to take 13 or
30. Okay, that will be a disadvantage, but it's not the end of the world. Do you have a tool that you like to use?
Do you mean like programming ones?
Yeah.
Not that I
Excel?
use for research.
MATLAB?
Okay, so it's the same kind of thing.
Yeah.
Okay.
Other question is some on Jupyter. We have to use that programming.
I'd like you to, but use what you're comfortable with and good at.
I was like, if I did on paper and like I post the paper, right, and I attempt it on the Jupyter theme, but I still like take points off. We take points off if I got it wrong on the programming, but
Probably not.
so make sure.
Alright, so my is on Blackboard. My paper and so we don't
Have to write on a whiteboard. I don't.
The paper and the computational tool that you use.
No.
So we do not have to only use the
on like a red chalkboard
JavaScript
for like 5 minutes and no one can read
Or
it.
the,
So it's like-
the online update.
If you have something you are more comfortable with,
We can use basically whatever.
use MATLAB, Excel. What do you do? MathCAD. Handwriting and do it, but
Okay,
at least pretend to try.
all right. I think